Hello everyone, welcome to the module on generative AI and large language models. My name is Mohit and I'll be presenting along with Rishabh and Faizan. The agenda of this module is as follows. I'll start with the introduction to the topic, and then Rishabh will guide you through transformer architecture and how these GPT models are trained. Then I will talk about fine tuning and prompt tuning LLMs, following which Faizan will talk about evaluation metrics, ethical considerations, real-world applications of LLMs, and finally, recent advances and future of generative AI. And we'll conclude the talk after that. Okay, so let's get started. Recently, there has been a lot of hype around AI, right? In news, in at least last 2, 3 years, we have seen a lot of things about AI. But if you think about it, AI has been around for a while. Back in 90s, uh, there was an algorithm called Deep Blue, which defeated that time's chess champion Gary Kasparov, which was an AI algorithm. If you go to any website where there is some recommendation for you, it is generated using algorithms which are powered by AI. If you scroll any social media web page like Instagram or something, it uses generative AI. A lot of products like Alexa and these automated bots, they are also powered by AI. So what exactly changed, which made AI in such a limelight in the last few years? So let's go through this timeline. AI itself, this term was coined back in 1956. And in 1964, the first uh, chatbot was created, which was a very simple rule-based algorithm. After that, in 1982, a new type of neural network was proposed called recurrent neural networks, RNNs, which could easily work with series of data. Then in 1997, as I said earlier, Deep Blue defeated that time's world chess champion Garry Kasparov. In 2006, we saw in a series of paper by big researchers like Jeffrey Hinton, this introduction to deep learning came, which led to a lot of improvement in AI. In 2013, word embeddings were introduced using algorithms like word2vec, and this was a interesting introduction, since these embeddings were basically used to represent words, and these embeddings were not just random vectors representing words. They could encompass the meaning of the word in itself. So, for example, a very famous example that people give from this time is that if you take the vector representing a king, and if you subtract the vector representing men and add the vector representing women from king, then you will get a vector which is very similar to the vector of a queen. So in a way, these vectors representing these words were not random. They had like some meaning which was encompassed in it of that corresponding word. Then recently, by recently, I mean like 7 years back, uh, Google introduced this transformer architecture, which was again a game changer, because all these new LLM models, what we see today, are based on this transformer architecture. Immediately after that, Google also released its first model, which was based on this architecture called BERT, which was performing really well at that time. And since then, we have seen like a series of large language models which have been published by different companies. But the game changer was OpenAI when it released its GPT models, where they used a new way of training these models using human feedback. And since then, we have seen a lot of companies building these models, like Llama from Meta, Gemini from Google, Claude from Anthropic. all these have come around. So what exactly happened in these last few years which led to such rapid development of these models? I would say there are like three important factors to it. One is, of course, the transformer architecture, which led to like developing these models, which are all based on this architecture. It enables efficient parallel processing and superior performance compared to previous models like recurrent neural networks and LSTMs. Uh, then we have also seen a lot of increase in computational power and data availability with inventions like GPUs and with internet, like so much data is available for training these models. So it becomes more and more efficient to train bigger and bigger models. And as you can see in this image, the size of these large language models has been increasing exponentially in the last 5 years. The latest models by the big companies have parameters in the approximate range of trillions. And but if you go back like 6, 7 years back, it used to be like hundreds of millions. So so it has increased a lot in the last few years. And again, there was this interesting technique of training these models called reinforcement learning from human feedback, which was introduced by GPT, Chat GPT model, which was uh, introduced by OpenAI. So yeah, so we'll talk about these transformer architecture and reinforcement learning from human feedback in the next section. But before that, let's quickly understand what exactly is generative AI and how does it sit with respect to the broader field of artificial intelligence. So generative AI is a type of machine learning algorithm, and this is basically used to analyze large amounts of data, and it kind of identifies the patterns and relationships between data, which can then be utilized to generate new similar data. Now, this is not limited to text. This can be images, audios, videos, codes. Uh, all of this will come under the category of generative AI. Now, LLMs are kind of are like generative models which are focused on uh, text data. So most of the time when we see these algorithms like GPTs and all, they mostly work with text. So these are large language models. But nowadays we are also seeing multi-model generative models. So for example, the new Gemini models, and even like some other models from OpenAI like Sora, they can work with like text, videos, images. So now we are seeing new generation of generative models which are multi-model. So they work with combination of different data types. Okay. So I'll quickly talk about a little bit about the applications of generative AI, which is mostly seen in the field of natural language processing. So one obvious field which most people talk about is in the domain of content generation, like generating new text in some field, or summarizing the data, classification of text, right? So these things are very common. Then one other very big field where it is used very frequently is the customer service field, to create like chatbots or like personalized recommendation, automated responses. Then these are also being very innovatively used in other fields like healthcare, finance, education. For example, in education, people are building these bots which can tutor you on a certain topic. So if a student needs a personalized tutor based on some subject they are trying to learn, these bots can help them in understanding the topic more deeply. Yeah, so So these are some broad fields where Gen AI is used. So it's not really limited to text generation, summarization, but people are using it in very innovative ways in different fields. So now Rishabh will talk a little bit about transformer architecture and how these models are trained. He will introduce the GPT series models, and then I'll talk about prompt tuning and fine tuning these models.
We have already looked into the introduction to generative AI and LLMs in the last session. We'll now move into the next section where we cover the different transformer architectures, various pre-trained LLMs, uh, which came pre and post the ChatGPT era, and also take a sneak peek into multimodal LLMs like Flamingo and Clip. Here's what we have lined up for the session. Uh, Firstly, we'll have a look at the transformer architecture. We'll look into the transformer architecture, how the transformer architecture works, its key components, and why it has become a key game changer in the field of natural language processing. In brief, we'll also cover various variants of the transformer architecture and also look at the evaluation of the transformer models. We'll also look at the pre-trained LLMs that came before the ChatGPT era, such as the GPT series, the BARTs, the BERT model, T5. We'll also look at the recent open source LLM like Llama and different versions of it, and how every day a new LLM is coming up and changing the scenario. Finally, we'll look at the multimodal model architectures like Clip and Flamingo. By the end of this session, you'll have a deeper understanding of these concepts and how they contribute to the rapidly evolving landscape of AI. Let's dive in. Let's start with the core of the modern generative AI, the transform architecture. It is a sequence-to-sequence model that eliminates the need for convolutions and recurrence. Instead, it relies on the attention mechanism, specifically self-attention. It consists of an encoder and a decoder model, encoder and a decoder module as depicted in the diagram. It was introduced for the task of machine translation, wherein the encoder task was to encode the input source language text, and the decoder will generate the translation in the target language. At the heart, the transformer is a self-attention mechanism, which allows the model to weigh the importance of different words in a sentence relative to each other. This mechanism involves the model to capture long-range dependencies more effectively than previous architectures like RNN and LSTMs. One of the key advantages of the transformer architecture is it is parallelizable. Unlike RNNs, which perform word processing sequentially, transformer can process all words in a sentence simultaneously. This makes the model significantly faster to train and more efficient in handling large datasets. Transformers are particularly adept at handling long sequences. The self-attention mechanism ensures that the model can capture relationships between distant words, which is a limitation in model that rely on recurrence. Now we'll look at the various variations of the transformer architecture and how it has evolved with time. Uh, Encoder-only models. They leverage only the encoder part of the transformer, excluding the decoder part. They're especially used for encoding text and doing predictions on top of it by adding peripheral layers like multi-layer perceptrons, RNNs, etc. Tasks like sentiment analysis, name entity recognition are ideal and suited with this model architecture. This is trained using a denoising objective like the mass language modeling, aka MLM, wherein tokens in the text are masked with 15% probability, and the objective is to predict the masked tokens. Pre-trained models like BERT and Roberta uses such a model architecture and objective. Uh, The next variant of the transformer architecture is the decoder-only model. They are used specifically for generative tasks like question answering, text completion, text summarization, reading comprehension. They're trained using causal language modeling tasks, which is an auto-regressive task. Herein, we, we feed a prefix text, and the objective is to predict the next token, which is the most likely token, uh, given it has learned it has the knowledge of the English and the linguistics of the particular domain where we want the model to adapt to. Pre-trained LLMs like GPT, Bloom uses this architecture. Next, let's dive into the pre-trained LLMs that were introduced before the ChatGPT era. Specifically, we'll look into the GPT series, we'll look into the BERT model, we'll look into T5. We'll also look into the algorithms like instruction tuning, RLHF in detail. So now let's talk about GPT-1. This was the first in the series of generative pre-trained transformers by OpenAI. One of the significant challenges in natural language processing has been the lack of labeled data. GPT-1 addresses this by leveraging a vast amount of unlabeled data text available on the internet for its initial training phase. GPT-1 utilizes the decoder model of the architecture. This means it focuses on generating text by predicting the next word in a sequence, a task well suited to the autoregressive nature of the decoder. GPT-1 employs a two-stage approach. Stage 1 is unsupervised pre-training. In this stage, GPT-1 is pre-trained on a large corpus of unlabeled text. The model learns to predict the next word in the sentences, capturing a wide range of linguistic patterns and contextual information. Stage 2 in this process is supervised fine-tuning on labeled data. After pre-training, GPT-1 undergoes supervised fine-tuning on labeled data specific to various NLP tasks. This fine-tuning helps the model adapt to specific requirements of the task, like sentiment analysis, translation, or question answering. Uh, okay, so now let's shift our focus to BERT, which is another influential model in the world of NLP. So let's look at the training task for BERT. The first task it is trained is on a mass language modeling task. During pre-training, BERT uses mass language modeling, where some percentage of the input tokens are masked at random. And the model is trained to predict these masked tokens based on the context provided by others, non-masked tokens. This allows BERT to understand the context in both directional, hence making it bidirectional. And the second task it is trained in, the next sentence prediction task. So the task here is the model to make the model learn to predict whether a given sentence B follows sentence A in the text. This helps the BERT understand the relationship between sentences, which is crucial for tasks like question answering, natural language inference. So if you look into it, BERT also involves a two-stage training. Stage 1 is unsupervised pre-training. So like ChatGPT, like GPT-1, BERT undergoes a pre-training phase on the large corpus of unlabeled text. During this stage, the model learns general language representation. Stage 2 is supervised fine-tuning. After pre-training, BERT is fine-tuned on specific NLP tasks using label data. This is the same supervised fine-tuning that was performed for GPT-1. And again, this second stage fine-tuning involves less data and again fine-tuning specific heads of the model like multi-layer perceptrons, and the rest core of the model is frozen. This was the same case with GPT-1, which I think I missed. Here again, the model is pre-trained, which is this blue part of the model is pre-trained. And then while fine-tuning, which is the second stage, the this part, the transformer part, which was already been pre-trained, is frozen, and just the peripheral part, which is a linear multi-layer perceptron, is fine-tuned on the specific task. This the fine-tuning process is very lightweight, and secondly, it requires very less data. So this was a complete game changer in the field of NLP, uh, where the biggest problem has always been the lack of label data for tasks like entailment and similarity. Uh, so this inspiration typically came from the ImageNet paper, wherein uh, this paradigm was already being followed in uh, images, and for the first time, GPT-1 was the pioneer in adapting the same approach to something like NLP. Now let's look at T5, which stands for text-to-text transfer transformer. Unlike the other models that we have seen, it uses an encoder-decoder architecture, which is a typical transformer architecture we have seen. This is from Google again. T5 reframes all the NLP tasks into a unified text-to-text format task, uh, treating tasks like classification, name entity recognition, summarization, question answering, classification, all as a generative task. And if you see, it's trained on a huge C4 dataset, which is a 700 GB corpus of clean web text, enabling the model to learn diverse linguistic patterns. During fine-tuning, T5 uses task-specific prefixes to indicate the required tasks, such as translate English to French for translation, or summarize for tasks like summarization. Even regression tasks uh, are also treated as text generation here, further unifying its approach across different tasks. Now let's discuss GPT-2. So GPT-2 uh, again increased the model capacity to 1.5 billion and also increased the amount of pre-training data used. They used a much larger pre-training data for language understanding and intelligence. A standout feature of GPT-2 has been the zero-shot learning capabilities, and to it can understand and perform tasks using only the instruction provided without additional task-specific fine-tuning. GPT-2 uses a pre-training objective similar to GPT-1, focusing on predicting next sentence, next word in a sequence, allowing it to learn from vast amounts of unlabeled text. OpenAI trained various variants of the model with different parameter sizes like 117 million, 345 million, 762 million, and 1.5 billion. Uh, they noticed that each subsequent model leads to lower loss slash perplexity than the previous one on the test and the train set. And the same has been depicted in this plot here. If you see, as they increase the model size, they see a consistent decrease in the perplexity. Uh, this is a great observation, a great scaling law that they develop, which through which they have been able to predict the performance of the language model with as they increase the size. And this was a great step forward for something like a chat GPT. So they could predict well in before time what is the performance of the model going to be, since they already see a pattern emerging. So so noticing this pattern, they move into GPT-3, wherein they increase the size of the model to something like 175 billion parameters. That's a staggering increase in the number of parameters. One thing they explored here is in context learning capabilities, wherein we feed exemplars to the model to learn from, along with instructions. So, in context learning involves no fine tuning and just feeding in examples and instructions, and the model will adapt to the task. And this is something they've noticed that as they increase the model size, the model gets good at following instructions and following the patterns provided in the examples. Uh, So this is being shown in the diagram here. If you see, zero shot in context learning can be of three types. One is zero shot, one is one shot, and one is few shot. In zero shot, they provide a task description or the instruction, which is to translate English to French. And then the prompt is given as cheese and please, and the model expected to provide the French of cheese. In one shot setting, apart from the task description, an example is also provided, but only a single example. And then the final input is given for which we expect the output. In a few shot setting, if we see, we provide multiple examples here, three, and again the third input and the last input is provided and the output is expected. This is different from a traditional fine-tuning method, which is not used for GPT-3. In a traditional fine-tuning method, example or exemplar is used to do a gradient update on the model, wherein the weights of the model are updated. Well, this leads to increased cost, need a lot of label data, and can lead to catastrophic forgetting. So, yeah, like with the advent of something like in-context learning, we can easily adapt our models to new tasks by human curating something as much as like 4 to 5 examples and solving a task. So this is what all the capabilities in the current LLM scenario is due to this particular uh, methodology that GPT-3 came up with. Next, we look into the Instruct GPT, which was a paradigm shifting model in terms of increasing the capabilities of GPT-3. So while GPT-3 was good, it showed signs of good instruction following and few shot learning. It wasn't great. It will still output text which differs from the instruction given, and uh, it can still lead to random sentences which can be random words which are completely incoherent to the input prefix. So they introduced Instruct GPT, and the idea was to uh, increase the instruction following capability. So Instruct GPT excels in following instruction with great precision and accuracy compared to its predecessors, GPT-3. This advancement is crucial for application requiring detailed and specific task execution. So Instruct GPT uses uh, again is firstly pre-trained on raw level data, as has been the previous version of GPT. But apart from that, there are two stages of pre-training. It happens with Instruct GPT. One is supervised fine-tuning, which is typically to generalize the model to follow unseen instruction. And second is RLHF, which helps in providing more safety, alignment, and helpfulness to the model. We'll look at all these, the different stages of training in the subsequent slides. So let's look at the 4-stage training. So we've already talked about the pre-training stage, which typically is a language modeling task on the raw internet data. This has to be a large amount of data, trillions of words, and the idea is algorithm is just to predict the next token. This is a base model, and it is the most time-taking part of the pre-training. Next is the supervised fine-tuning, which we'll talk about. Here, we collect ideal assistant responses, which are typically human curated and uh, very carefully curated by humans. Sanity of the data set is paramount here. Around 10 to 100K prompt to response pairs are written by contractors, and they have to be of high quality. Next, again, the task and the algorithm remain same. That is that of language modeling, which is to predict the next token given the prompt. This is typically This is not as expensive as the pre-training phase because the number of um, data size is smaller here, and Iguana actually just stops at supervised fine tuning. Next is the RLHF phase, which in turn incorporates the reward modeling and the reinforcement learning. Yeah, so the first is training a reward model and human comparison data. And the second is training the language model to generate responses such that the reward of the response given the input prompt is maximized. The training happens here using a PPO algorithm. We'll not dive into the details of PPO because that's beyond the scope of the session, but it is an RL algorithm that is being used, and we'll see the RLHF method more detail in the next slide. Okay, before going to RLHF, we'll look at the example of supervised fine tuning. So this is how the prompt and the text, which are human curated, will look like. So what is the capital of France? There will be ideal response like the capital of France is Paris. What is the best way to learn a new language? And then humans will annotate and write the most important, most appropriate response to it. So these are very simple examples, but in reality, more complex examples like mathematical reasoning and logical reasoning and Olympiad problems will be there, code will be there. So it is important here that we show the model all the different type of tasks that it could encounter during inference. This will provide a general ability of the model to follow complex instructions. So note that this is the most important part. RLHF will also lead to improvement of instruction following, but that is more inclined towards alignment and safety, which is an important criteria, right? So the next stage is RLHF, that stands for reinforcement learning with human feedback. We firstly describe the process to train the reward model. So a prompt is sampled from a data set. Uh, and various and several model outputs are sampled for the particular prompt. And note that the model is the model which is trained using the supervised fine-tuning data. So supervised fine-tune model in the last stage. And so for a given prompt, we sample different variants of the same prompt, variant of answers for the same prompt. And a labeler, so the different answers could be due to different checkpoints of the model or changing the temperature, which can lead to sample tokens from the top 5 or top 10. So various strategies are there to uh, sample different answers. So that is something we don't want to cover right now, but something will be covered later. Uh, so a labeler will rank the outputs from the best to worst. A human labeler will rank these outputs. And this data is then used to train a reward model uh, using a ranking loss. Next, the policy, that is the supervised fine-tuned model, is fine-tuned to maximize the reward on prompts sampled from the data set. And this is done using the PPO algorithm, which is a reinforcement learning algorithm. So firstly, a new prompt is sampled from the data set. The PPO model is initialized from the supervised policy, which is the step 1 policy. The policy generates an output. The reward model calculates a reward for the output at the real time. And the reward is then used to update the policy using PPO. So that's how the 4 stages of training for Instruct GPT looks like. So till now we have looked into Struct GPT. So Instruct GPT is typically GPT 3.5, which is Code DaVinci 002, and further instruction tuning and RLHF on it led to ChatGPT. Note that while instruction GPT was trained on single turn data. ChatGPT is trained on multi-turn data. This provides it the capability to understand dialogue context and maintain coherency of the output. Now let's look at GPT-4. So GPT-4 is multimodal and it can accept both image and text prompts. Uh, we are still not sure how the training of GPT-4 has happened, uh, and that too in a multimodal setting. But we do know that it is still fine-tuned using supervised fine-tuning and RLHF. Uh, it has even larger architecture as compared to Instruct GPT. It There are speculation that it follows a mixture of expert architecture, wherein there are different experts to solve for a different task, and there's a routing mechanism guide that would basically invoke different experts uh, depending on the task. GPT-4 improves significant improvements over GPT 3.5. So we'll look at the evaluation results now. So here are the results of here we compare different models like GPT-4 No Vision, and GPT 3.5 on examination, how they perform on different examinations. And these examinations are mentioned in the x-axis, and in the y-axis we show the percentile uh, scored by the different models. Uh, the ranking is basically the order of the exams are basically uh, the performance of GPT 3.5 on the exams. If we see that GPT-4 surpasses the other models on in most of the exams, and even achieving 100% percentile scores on some of the exams. Okay, so now we'll look into the recent open source. Okay, so now we'll look into the open source uh, recent LLMs like Llama. So Llama has been developed by Meta AI. It uses a decoder-only architecture, uh, which has been used by GPT uh, all all the while, and they also adopted the similar architecture. Um, Llama is trained using publicly available data sets, ensuring broad foundation of knowledge and applicability across diverse domains. This approach facilitates transparency and accessibility in AI research and development. So Llama scales its parameters from 7 billion to 65 billion, offering flexibility in model sizes depending on the complexity of the task. This scalability enhances its capability to handle varied level of computational demand and task complexity. Despite its smaller size parameter range compared to larger foundation models like GPT-3, Llama demonstrates superior performance in certain tasks. This achievement highlights its efficiency and effectiveness in generating high quality outputs. Llama incorporates innovative properties such as RMS norm for stability, SWI glue activation functions for improved computation, and rope, which is rotatory positional embeddings for accurate context handling. These features contribute to its robust performance across different natural language processing tasks. In this table, we showcase the performance of Llama model with respect to the several contemporary models at that point of time. If we see that Llama outperforms various uh, bigger models like Palm and GPT-3 on datasets like Pika, SIQA, HelaSwag, and OBQA, they focus on the fact that having a cleaner data and more diverse set of data rather than having more similar set of data uh, can lead to better performance and more efficiency in model training rather than just uh, making a bigger model uh, while and having a lot of data. So that's what they focused on. That has been the performance, the philosophy, with the different versions as well. Here we discuss about Llama 2. Llama 2 has been trained on 40% more data than Llama 1, and it has double the context length. Uh, Meta introduced different model sizes for Llama 2, such as 7 billion, 13 billion, and 70 billion. Llama 2 has been pre-trained on 2 trillion tokens. Uh, and also, they, along with the pre-trained version, they also, this time around, introduced the chat version of Llama 2, uh, which is known as Llama Chat. So it has been undergone through supervised fine tuning over 100K data samples. And it has also been trained using RLHF over human preferences uh, on over 1 million data size. So this is how the training of Llama Chat has happened. The first thing is pre-training. The process begins with pre-training data, which undergoes self-supervised learning to create the base Llama 2 model. Uh, Then the fine tuning phase happens. The Llama 2 is then uh, fine tuned through supervised fine tuning to produce Llama 2 chat. Next is human feedback. Human preference data is collected and used to create two reward models, as shown in the diagram. First is the safety reward model, the second is the helpful reward model. These two models feed into the fine tuning process. Uh, So then comes the RLHF phase. This stage involves two key components. First is rejection sampling, and next is proximal policy optimization. These elements work in a cycle with Llama 2 chat, continuously refining the model. The entire process forms a loop, with the final Llama 2 chat model potentially feeding back into the final rounds of human feedback and fine tuning. This comprehensive approach combines machine learning techniques with human input to create a chatbot that's both capable and aligned with human preferences for safety and helpfulness. Next, we'll look at Llama 3. So Meta introduced two variants of Llama 3. One is the 8 billion and the other is the 470 billion parameters. And they increased the vocab size of it to 128K and also double the context length from 4096 to 8192, uh, leading to more supporting more larger prompts and uh, being able to take as input more bigger documents. It is trained on 7 times larger training data set as compared to Llama 2. Also, 4 times more code data has been used to train it. Another thing is that Meta has claimed that they have been training a 400 billion plus parameter model, which is a bigger, way big version of Llama. They have also shown that it is multimodal and has vision and audio capabilities. They've also emphasized on multilingual capabilities of the model for broader applicability, and they've also promised a larger context window. Uh, so Meta also has released the performance data for the new Llama 3 model, showcasing impressive results across various benchmarks and comparisons. The pre-trained model performance is presented for different sizes. Llama 3 8 billion outperformed Mistral 7 billion and Gamma 7 billion on several benchmarks, including MMLU, AGI Eval, Big Bench Hard, ARC Challenge, and Drop. Llama 370 billion shows even more substantial improvements, surpassing Gemini Pro 1.2 and Mixtral 8 cross 22 billion on the same benchmarks. We also present human evaluation results for Meta Llama 3 70 billion instruct. It wins 52.9% of the comparisons against clothes on it. It outperformed mixed and medium in 59.3% of the cases. Again, GBT 3.5, as we see, it wins 63.2% of the time. When compared to Metalama 2, it shows a 63.7 win rate. These results indicate that Llama 3, especially the 70 billion version, is highly competitive with other leading language models in both automated benchmarks and human evaluations. Now let's dive into some multimodal architectures like Clip and Flamingo. So far we have mostly concentrated on text-to-text model, which takes as input textual prompts and outputs textual responses. But with just text, we are constraining our uh, the amount of data we are feeding to the model. And with multimodality, we expect to uh, power into the model different other modalities like text and images, which allows for more the model to see more data and being able to generate different type of modalities. So first we'll discuss about clip. Uh, now let's talk about clip, a powerful model developed by OpenAI. Clip leverages contrastive learning to align text and images. This approach allows it to understand connections between textual description and visual content. For a given set of images and its corresponding options, the text and image encoder are used to come up with its corresponding embeddings as shown in the figure. So as we see here, given a set of images and a set of text, which are the corresponding captions for the images, here we have two encoders. One is a text encoder and one is the image encoder. These are uh, randomly initialized from scratch. And these text encoder will encode each of the text here, and the image encoder will encode each of the images there. And then we come up with this matrix, which basically contains the dot product or the similarity between each of this text and the image pair. Now, through contrastive learning, we try to maximize the diagonal elements, which is the appropriate pair of image and text are, like forced up while the, like the wrong pairs are forced down. This is a typical contrastive learning setup that is being used here. Note that such an architecture allows for zero shot inference. So suppose we have an image, new image, and a set of classes. We can use this image encoder to encode the image. Similarly, the set of classes could also be encoded using the text encoder. Now, the semantic similarity between the image embedding and the text embedding will be taken, and the semantics and the text with which the semantic similarity is the highest will be used to will be used as the class for the particular image. Note that such a setup doesn't require uh, can generalize to any new classes because we have there's no multi-class classification sort of setup that is happening here. So this allows for zero shot image to text or text to image classification during inference. So now let's look at Flamingo, which is a visual language model, uh, and uh, and that operates not only on text but also on images. VLMs or visual language models can process both images and text and enable tasks such as image captioning, visual question answering, and text to image generation. So Flamingo is a type of visual language model developed by Google DeepMind. Let's look at the example here. In this example here, we see a series of images that has been fed to the Flamingo model here, wherein a person is trying to catch a ball, and at the very step, and these are the series of images which has been fed sequentially, and then a textual question is being asked, like what happens to the man after hitting the ball? And the model correctly predicts that he falls down. Similarly, there are other cases, like if you see here, there is a picture given, and the Flamingo model correctly says that this is a picture of two teddy bears on the moon. And then the user will ask follow-up questions, and the model is able to correctly, like comprehend to the input and provide the right output. So we can go through each of the cases here. Yeah. So now let's look at the model architecture that has been used for Flamingo. So this is primarily built on top of a typical text-based transformer architecture. So we will have a text-based transformer architecture, and we'll have a vision encoder, which could be based out of, say, a ResNet or a visual transformer. It could be anything. Note that the blue layers means they are pre-trained and frozen. So if you look at the large language model blocks, which are in blue, are frozen, and so are the visual encoder blocks, which are frozen. New layers, which are trained from scratch, are shown in pink, and these are the perceiver resampler and the gated cross-attention dense layers. Uh, so, so what happens is that the input is provided. Say this is the input, which contains this is a very cute dog, and then the model is given an input of image, and it is asked this is a. And if you see, the image and the text is interleaved as shown here, and the images are then uh, like th- this is how it is provided to the uh, to the language model. Like the image is converted into this image tag, and then the images are passed to the vision encoder to get the image embedding, and then they are passed through the perceiver resampler, which reduces the dimension of the embedding, and then they are fed directly to the gated cross attention dense layers. So what this gated cross attention dense layer do is that it takes a cross attention between the uh, language queries and the visual key and the query value. With this, the model is able to like basically it is not only attending to the uh, textual key and the key and the values, but it is also attending to the visual inputs. And this is powered through the adapter layer, which is introduced in the form of a gated cross attention layer. Okay, so now we have looked into the multimodal architecture. Now we're coming to the end of the session. Here we'll show we'll look at the current LLM leaderboard. This is the leaderboard provided by LMSys Chatbot Arena, which is an which is a open platform for LLM evals. It uses over 1 billion human pairwise comparisons to rank LLMs. Currently, GPT-4o is at the top with Claude 3.5 on the second. And then Gemini Advanced, Gemini 1.5 Pro, GPT-4 Turbo, and the rest of the model. Note that most of these models are multimodal. In fact, all of them are multimodal. And this is a very dynamic arena, and every day one model is topping the other, and it's a very dynamic field. So with that, we have come to the end of our session. So what we have done here, we'll just take a look what we have seen in the session. We have introduced the various transformer architectures, various pre-trained LLMs before ChatGPT that led to it. We also discussed post-ChatGPT LLMs like Llama series. We took a sneak peek into multimodal models that operate both on images and text like Flamingo and Clip. We looked into the current model scenarios on the leaderboard. So that's what we looked at. Next, we'll look into techniques of prompt tuning and fine tuning LLMs. Uh,
Hi, now we'll start on uh, seeing how LLM models can be used for your specific task. So now that you have already seen how these LLM models are trained and what kind of things are required to train these models, now we'll see like when do you really need to train a model and when can you get away with some simpler methods to use these LLM techniques. So consider this problem statement where you want to develop a chatbot which can answer questions related to your website. Now, there are few options here, right? One is you train a model from scratch on your data, similar to how these LLM models are trained. The downside is that you will require a huge amount of data, huge amount of computation, which will lead to requirement of good capital, like millions of dollars to train a huge large language model. Second option is you use an existing LLM as it is. So you just take the APIs of one of these LLM and just give it the query and ask it to answer the question. The problem with that approach is that it might not be tuned to the data which is present on your website. So, for example, people asking questions very specific to your website might not be able to answer, or it might even hallucinate to generate some random answer based on the training on the world data. Now, there is a third option, which is fine tuning an existing LLM on the data from your website. Now, this is a more reasonable option since this allows you to tune the model for your specific use case. And the second thing is it does not require a huge amount of investment, computation, and data. It can be done with very less amount of data compared to, let's say, training a model from scratch. Even simpler option is to do prompt tuning, where you can somehow include examples from your website and tune it to kind of answer the queries in a way that you want it to. I'll discuss it in details what each of these steps mean. And finally, one of the approaches which is used most is RAG, which is retrieval augmented generation, where you use a retriever to get data from your website for a query and then use an LLM on top of it to generate a answer. So I'll discuss these three approaches: fine tuning, prompt tuning, and RAG in more detail. So let's just start with the fine tuning approach. So in fine tuning, what we do is we take a pre-trained LLM and then further train it on a specific uh, and often much smaller data set so that it can adapt it to that particular task. Now in this figure, you can see like the base LLM is a pre-trained model, which is trained on a giant corpus of data from internet. And then you take the domain specific data and you fine tune it. Uh, and then you get this fine-tuned LLM, which user can uh, interact with to get response for their queries. Now, what is the purpose of this? Like this improves the model performance on that specific task. It reduces the need for extensive training from scratch, which is often a huge bottleneck for a small company or an individual. And it customizes the model to understand domain-specific terminology and contexts. Okay. So let's uh, see in more detail uh, how fine-tuning helps in general. So it leads to, as I mentioned, enhanced performance. How it does it is that you take the pre-trained models and then since you train it on the domain-specific data, it is able to adapt the underlying LLM for that specific use case. So, for example, if you are doing a medical diagnosis or something, and if you just ask existing LLM some queries, it might not be able to understand the technical jargons or the details which are often used in that kind of medical diagnosis. But if you use a existing LLM and use a lot of data from that particular domain to fine tune it, it leads to much better performance. So for what fine tuning basically does, it changes the parameters in the model. So it's just like training, but on top of an existing LLM model. It of course is, as we need much less data and much less compute to fine tune the model. It is much more effective in terms of both cost and data. And it has the ability of domain adaptation, and it's very fast. So like training the models can take weeks, but fine tuning can be done in hours. So you can quickly adapt an existing LLM to fine tune it for a domain specific task, and it becomes usable for that particular task. So these are the main differences in terms of four different dimensions. As I mentioned earlier, like pre-trained models use a huge amount of data. Fine-tuned models use much less data. Training time is again a big factor here. Cost again, like individuals and smaller companies it can be very difficult for them to use to train a model from scratch. And compute is a direct reflection of that. If you want to train a model from scratch, you will need a huge amount of compute. So let's see what really happens in fine-tuned models, how it helps. So here is a example. So on top, you are seeing a model which is trained on terabytes of data, which is the pre-trained model. And if let's say it's trained on a bunch of data, as shown there on the left is the input to the model, and then on the right is the output from the model. Now, let's say what we want to do is use this model so that if we ask it a query, something like when was Barack Obama born, we want it to simply answer the year. So in this case, it would be 1961. Now, the model doesn't know like what kind of output we specifically need. But since it is trained on this whole internet data, if we ask this query, it will probably know that Barack Obama was born on August 4, 1961, but it just doesn't know that we need only the year, right? So what we can do, we can create such data sets where we ask it what are the when was someone born, and then the output is the year, and we fine tune the model on this data. So we are in a way utilizing the underlying understanding of the model, which it already knows. Like when someone was born, it just doesn't know how to output the just the year. So we fine tune it on this particular task, and it becomes tuned in this specific task, and then we can use this fine-tuned model uh, to then query about someone's birth, and it will output the year. And as mentioned earlier, this will require much less data to fine-tune the model mm, uh, compared to the option of training it from scratch. So the first step which is required for fine-tuning is the data selection. And there are few aspects of data that you must keep in mind when selecting it for fine tuning. So first is relevance. The data should be relevant to the specific task that you want to fine tune the model for. The second is quality. The higher the data quality, the better will be the output from the model, right? So if you believe that there can be errors and duplicates or like irrelevant content in the data, you should clean the data and remove the noise, which will improve the model performance. Then comes the diversity. The more type of examples you'll show corresponding to the task you want to handle, the better the model will adapt to those tasks. Size of the data, as is the case with most models. If you ensure the data set is large enough uh, to capture like the intricacies of the task, it will be able to learn that in a better way. If you don't have enough data, people also nowadays use augmentation, where they use these LLMs, in fact, to generate synthetic data, and then they add it into the data set before training. And of course, as is with the case with any new technologies, you must consider the ethical side of the task you are tuning it for. Be mindful of the potential biases in your data, so that when someone uses your model, it does output something which is fair and not biased. Okay. So now, as I mentioned earlier, like fine tuning, the model parameters are updated, right? Now there are, as I mentioned in the introduction, nowadays models have trillions of parameters, right? So one option is to, of course, just train it on this new data set and just let it update any parameter which is there in the model, right? However, people came up with some very interesting techniques to even further optimize it and reduce the compute and while keeping the performance kind of similar by introducing this parameter efficient fine tuning. Now, what it does, it kind of modifies a small subset of the model parameters. So most of the parameters in the models are kind of uh, frozen, so they don't change. And a small subset of the data of the parameters can change based on the new data on which it is trained. It, of course, offers less flexibility compared to full fine tuning, uh, but at the same time, it allows for even lesser compute and leads to very close performance compared to full fine tuning. Some of the common methods which are used in these are uh, adapters, low rank adaptations, and yeah, as I mentioned, freezing large parts of the model. So let's see uh, what is really parameter efficient fine tuning and how it helps. So yeah, these things I already mentioned that like these ML models, like if you see a pre-trained LLM models, as I mentioned, like these are like very complex models with trillions of parameters. And this tuning of these parameters are how someone tunes a model. It makes it behave in certain way, right? Now, instead of tuning each of these parameters, we'll see how we can tune a subset of parameters and still uh, attain a very reasonable performance. And again, the benefit is significant reduction in the computational and memory requirements. So as you can see here in this image, let's consider a model which has billions of parameters. And what we are showing here in blue is the parameters which we don't change. So these are the frozen weights in the model, and the red ones are something which we change. So as you can see, like a very small part of the model is tuned for the specific task. So basically what happens is when you have your data and you want to train this model, you do it same thing, gradient descent, but you don't change the frozen weights. You only make changes in the trainable weights, which is a much smaller percentage compared to the huge model. So one of the famous techniques which is used in this regard is low rank adoption. So here you see there are multiple paths to the model. Let's say we have a input of dimension d and an output of dimension k, and in between, let's say there is a uh, hidden layer where we have uh, two parts of it. One is the blue one, which is the frozen weights, and then there is another one which is the trainable weights shown in red. Now, on top of these trainable weights, what low rank adoption does is it uh, kind of decomposes this weight matrix into into low rank matrices. So consider this case like this these two matrices A and B. If you see, let's say A is of dimension D cross R and B is of dimension K cross R, sorry, R cross K. then the multiplication of these gives you a matrix of dimension d cross k, right? Now, what happens in low rank adoption, since we represent this whole d cross k matrix using multiplication of these low rank matrices, the number of trainable parameters reduces to d cross r plus k cross r. Now, if r is small, this is much less than d cross k. Now, this obviously leads to some reduction in the tunable parameters. Uh, However, this has been shown to achieve a very good performance and very much comparable to fine-tuning a large language model. So this is a very famous algorithm. And on top of it, people have also added quantization, where what happens is since these model parameters are represented using this 32-bit floating point, but in quantization, it is truncated to 8-bit or lower. So instead of having a very precise model parameter of 32-bit floating point, we reduce the precision, which leads to very like decrease in memory uses and increases computational efficiency. But at the same time, it doesn't lead to huge reduction in performance. So while maintaining the performance of the model, we are able to reduce the memory and computation uses, thus leading to faster training and less compute needed for the training. Okay, so as I mentioned earlier, uh, like pre-trained and fine-tuned models, in both of these, if there is an option, uh, most people go for fine-tuning since it is much less uh, requirement of much less compute and training time and training data and everything. But if you think about it, you still need to understand something about the model. You still need to uh, get data and train the models, and you still need a few GPUs to train these models, fine-tune these models. However, for some tasks, you don't even need to fine-tune the models. You can just design the prompt in such a way that you are able to achieve what you want to do in your task. So let's see what is a prompt and how it works and how it can be designed in such a way that you don't really need even fine tuning in most of the cases. So prompt is basically an input which is given to the LLM based on which it starts generating next tokens and thus generates the response, right? So for example, if you want to write a story about a robot, you give this prompt to the LLM, like write a short story about a robot discovering a new planet, and then it goes ahead and start filling next tokens, and a story gets built up, right? Uh, Similarly, if you wanted to explain some technical thing, you can ask it to explain the concept of blockchain technology. Now, these are very simple prompts where you are just asking the LLM what you need, and it starts generating the next token based on your query, and it gives you the answer. Now, these prompts can be very elaborate. Uh, so with every new version of the model, they also allow bigger and bigger prompts. So nowadays, I mean, for example, models like Gemini can take hour-long videos as prompt in the input, and you can ask it queries about the things in the videos. You can easily nowadays in the latest models from even from GPT, you can give it like a short book as input, and you can ask it queries regarding the book, right? So nowadays prompts can be very elaborate and very long. However, the short and crisp the prompt is, the better is the performance. If you keep increasing the prompt length, it leads to more time for the inference, and also reduces the performance. So it's better to write prompts which are crisp and contains all the information which is needed to answer or do the task which is supposed to be done. So let me give a little bit of uh, points on how to write good prompts. So the first thing is be clear and specific. So think of it as you are explaining someone to do a task, and the more precise and accurate you are in explaining your task, the better the job will be done, right? So, for example, instead of saying something like, is remote work good? Maybe you can ask more specific question like, what are the main challenges and benefits of remote work, right? Uh, if you have like a query, you want to understand something, you might say something like, what is photosynthesis, right? But if you want to understand this topic in like so that even a small child can understand, you can ask the LLM in the prompt that explain the concept of photosynthesis as if teaching a 10-year old. So you can provide the context in the prompt, right? You can also set the tone and style of the output. So instead of saying something like write a story about a cat, you can say write a funny story about a cat who thinks it's a superhero, right? So you have provided some context. You have also set the tone, like write it in a funny way, right? And another very important thing is you should include examples or templates whenever the task is complicated. So, for example, instead of saying something like review a new smartphone, if you want the review in a certain format, you should let the LLM know in about this in the prompt. Either you can explain it, like add these sections, like highlight the features, pros and cons, or you can also give it an example. Uh, for example, here you can see in the prompt, the new X phone is sleek and powerful. It features this inch display. These are the features, and it talks about the pros and cons. So these things are very important for writing good prompts. And there are also like tons of uh, blogs you can find out because people are still discovering new things about writing prompts. So this keeps on they keeps on adding things to improve prompt writing. Okay, so now like prompt engineering is what we have been talking about until now, where we are saying uh, like we should write good prompts. And the zero shot prompt is something where you just ask it to do something without giving any example. So for example, here you see that in the prompt we are saying translate the input text from English to French, and we give it the input, hi, how are you, and output we expect the LLM to fill it in, right? Now a one shot prompt is something where we provide a single example of what the task is. So for example, here you'll see that we give an example of an input and the expected output from the LLM, and then we give it the task. And usually this has been shown that this improves the performance of the LLM. Similarly, there can be few short uh, prompts where you add multiple examples. So usually if the tasks are more complicated, you should add more examples to kind of cover uh, different kind of intricacies in the task. Okay, then there is something called chain of thought prompting. This is also very interesting. Usually very helpful for tasks where some kind of logic is required. So for example, here you will see that if there's a question here about Roger has 5 tennis balls, he buys 2 more cans of tennis balls, each has 3 tennis balls. How many tennis balls does he have now, right? Now, if you just say the answer is 11, and then you ask another query and expect it to answer the query, it might be wrong. But when you are giving the answer for the first one, and you also explain how you arrived at the answer, which is 11, then if you ask a similar query, it's much more likely that the LLM will uh, be able to generate a correct answer. You can also simply add a line saying कि think about each step before giving the output. That also helps. Okay. So now Now, all of these things can help you improve the prompt, but these are all very manual tasks, right? You have to try different things for your specific task and see which prompts work for you. There's also something called prompt tuning, uh, where also the aim is to have like a prompt which can solve the task at hand, right? But here it's more like a technique where we want to optimize the prompt tokens, of course, rather than models parameters. But instead of doing it manually, this can also be automated. So one thing you should notice in the figure here is that in model tuning, uh, we are taking a bunch of data and we are creating different models for different tasks. So if let's say we have three different tasks and we have data for each of the tasks, we create three different models for each task by tuning it on that particular data. But in prompt tuning, what happens is we can take the same model but modify the prompts for each task by maybe it can be done by designing the prompt in such a way that if we want to solve a particular task, maybe we add examples from that particular task into the prompt, or we tune the prompt in such a way that it works for that task. But the underlying model, which is called for each of these tasks, remains the same. It's just that the prompt which gets modified. So, yeah, that's I think about prompt tuning. Now we'll see one other approach, which is very useful, especially for the task that we discussed earlier. For example, if you want to create a chatbot, let's say on which can answer the queries specific to, let's say, the data on your website. So there, this retrieval augmented generation RAG is very useful. So consider that you just went ahead and took an API from one of the existing LLMs and exposed it to the user of your website, and the user comes and asks what is Prime, right? Most likely, and this is a real example, I asked ChatGPT what is Prime, and it gave me an answer about Prime numbers. Although what I wanted to know here is what is Amazon Prime, right? So this chatbot is not really tuned for my data, so it took prime as the prime numbers from mathematics because that's a more broader topic that usually people ask for in a real world situation, right? But if someone is asking what is prime on Amazon, they are most likely asking for what is Amazon Prime and not what are prime numbers, right? So in these cases, RAG is very helpful. So let me quickly show how this works. So what happens is, let's say someone asks what is prime, which is the query here. Uh, what happens is it passes through an embedding model and an embedding of this query is created. And what is also done as an offline step is let's say the pages of Amazon are kind of stored in a vector database. There also we have the embeddings of different things, and then we match this query embedding with different chunks of data which are stored from the Amazon website, and then we find the, let's say, top K best matches, and then we use this as a context. So we give the query and this retrieved data from the Amazon website as the context to the LLM, and we ask it to answer the query. So what will LLM see is the query is what is prime. And let's say in the prompt, we say that while answering the query, use the following context. And in the context, since on Amazon website, we'll mostly find data about Amazon Prime and not Prime numbers, we'll retrieve data about Amazon Prime. So the LLM will have the context in which it has to answer the query, and the answer will be grounded into the context which we have retrieved from Amazon. So in a way, we have uh, used the LLM, we have used the language power of the LLM, but at the same time, we are able to kind of ground the answer into the context which is based on our website's data, right? So let's see here. let's say we ask the question, what is Prime? What will happen is that it will retrieve some relevant documents from Amazon, which are stored in terms of chunks. So what happens is you take like multiple pages from Amazon, let's say, and you create a small chunks and you just dump it in a vector store, a database, from where you can do like a match. So you find all the chunks which are very similar to the query asked. So you'll, in this case, you'll retrieve a lot of chunks which mentions Prime, right? And all of these will be talking about Amazon Prime. And then you give it to the LLM, and then the LLM's response is basically uh, about Amazon Prime and not Prime numbers, right? So yeah, so this RAG is very useful and is used uh, and it's quite popular kind of method for many use cases where you want to kind of ground the answer from the LLM for a specific task, and is a very simple approach. You don't have to do any tuning. You don't have to do any kind of uh, fine tune. You don't need really data to train anything. So very less compute is required. The only thing is like you have to kind of store the data in an efficient way, such that you can quickly do like a similarity search for the query that has been asked and retrieve important kind of chunks from the data and formulate the response. Okay. So now we have seen like a lot of like big range of approaches which can be used on top of the LLMs to kind of modify it or use it as like a base layer on top of which we build some other things for like our specific use case, right? Now, I'll quickly touch upon one more thing before Faizan uh, does the rest of the presentation, which is evaluating LLMs. Now, since all these approaches are used to kind of take LLM and modify it for our own use case, you have to like evaluate uh, the final model or architecture you come up with for your specific use case. And here it's a challenging task because evaluating the performance of these generative models is a difficult task. And depending on which task you are using it for, uh, it might not be possible to do a kind of automated evaluation. So for example, let's say in the case of creating a chatbot for your website, you have like a query from the user and then you generate the response, right? Now, how good is that response can only be answered uh, if you have a domain expert from who understands the data from your website, right? So usually people require human annotators to kind of evaluate the model performance. There has been a lot of work on doing automated evaluations as well, but these are not perfect. So people still do rely on human evaluations for many tasks. Now, to evaluate these models, you will require some data, right? So, for example, in this chatbot, you will need some examples of queries in the final response created by the chatbot. So you have to make sure that these this data kind of cover all the possible cases and not just kind of uh, come from like a very single part of the chat which will be seen when you deploy this chatbot. So it should be generalizable, it should be high quality. Test data should be accurate, right? If the test data itself has errors, it will be difficult to kind of rely on the evaluation. Uh, and yeah, in case of some of these techniques, you would also need that these test data are not really seen in training. So I mean, these LLMs are trained on internet data. So if you randomly take some internet data and you try to evaluate on that, You have to make sure that particular data was not part of the training, otherwise it's difficult. So that's why it becomes difficult to verify the reliability of these evaluations. And there are also some famous rankings which are more standard, like these ELO rankings, where top LLMs are scored based on ELO scores, which comes from some kind of it comes from like A/B tests by competing LLMs against each other. So you can look at it every time new models come. Uh, they do these rankings, and there's a leaderboard which is maintained, and it's based on like various tasks like reasoning, text generation, then translation. All these things are you can compute it on. So yeah, so now Faizan will take you through the rest of the sections. Thank you.
Hello and welcome back to the fourth edition of ML Summer School, and we are talking about the generative AI module. So we have previously looked at Introduction to Generative AI, GPT series of models, and prompt tuning and fine tuning. Up next, we'll look at the evaluation metrics and performance. So why do we need evaluation metrics? So we want evaluation metrics to evaluate the quality of the output of our LLMs. We want to see if the LLM is doing good or bad, how is it performing, and if its responses are acceptable or not. Now, the challenge with evaluation metrics in proper evaluation of LLM metrics is that you cannot have simple metrics like precision, recall, or F score, or accuracy evaluate the LLM metrics, right? Because LLM generate long text, so it's generating a long string of text. Now, how do you evaluate that long text and give out metrics that can actually give information about whether that long text is correct or not, right? So, because of that issue, we cannot use simple metrics which are like precision or recall, which only expect one output and one ground truth, right? So, we use some of the metrics which are based on the text domain. Okay. So, for example, here we have perplexity, blue, and rouge scores. Rouge is kind of like a recall metric where you have a question or a input to the LLM, and the LLM gives a response. You also have the same question, and you have a human response for it, and then you compare whether the LLM generated response is actually matching the human generated response by comparing the n-grams present in the LLM response and the human response. So if the LLM response has all the n-grams that are present in the human response, then the root score will be higher. So it's kind of like a recall metric, right? Similarly, other metrics like perplexity and blue also have this kind of logic behind them. Now, the other metrics we use human evaluation, right? So human evaluation is basically we try to compare the LLM output to another LLM or to a ground truth human, but the judge who judges whether the response is good or bad is a person itself. So let's say I would have you as a human evaluator. So you would sit in front of an LLM, the LLM will generate the response, then you will rate the LLM response. And if you rate the LLM response good or bad, based on that, we'll improve the LLM further, right? So that's human evaluation. Similarly, there are also task-specific metrics like summarization has Rouge, which we talked about as the recall kind of n-gram recall metric, right? N-gram recall between what the LLM's response was and what the original human written summary was, right? For code generation also we have similarly some metrics like is the code written correct or not? Is the code written readable or not? Okay. These are easy to evaluate compared to human evaluation, but still require different kind of evaluation than compared to precision and recall. So we use these metrics majorly to have an idea about how to do improvement and how to track progress overall in the field. Now I have shown you few of these links where you can go. OpenLLM leaderboard by Hugging Face actually shows the performance of various models on some very common ML tasks. Okay, and it helps you understand whether your model is good at some tasks or bad at some tasks, and then improve. Then similarly, chatbot arena is a leaderboard or a space where people ask a question and then two different LLMs will answer, and then they get to vote whether this LLM is better or that LLM is better. And then we can know based on the comparisons which LLMs are doing good in the current time, right? Then there are some common metrics that I told you, right? Perplexity, blue, win rate, which is this LLM winning more or this LLM winning more? Which LLM is winning more times? Okay, these are some of the common metrics for LLMs. Now, we did not talk about image generation, right? So, uh, modern day generative AI also is used for generating images. So, there is something called as FID metric, which is used for image generation, which is nothing but it uses a image backbone and takes the candidate image and the actual expected image and then calculates a distance between them. So, that is the FID for image generation quality detection, right? One of the common metrics, perplexity. So, perplexity is a metric which tells you whether the LLM is doing good or bad in generating natural text. What perplexity finds out is that uh, is the LLM able to generate the text that was in the corpus with high confidence. Okay. So lower the perplexity, higher the LLM's confidence actually. Like if you see this P of xi is the probability of the token. Okay. And if the LLM generates n tokens, then what is the probability of the correct token? So if the LLM is generating the correct token or giving very high probability to the correct token, then this probability score will be 1 and then this log 2 will become basically 0, right? So this whole log thing will be 0 and then you have 2 to the power minus whatever 0, okay, which is nothing but 1, right? So 2 to the power 0 is 1, right? So basically 1 is the lowest perplexity you can reach, and if the probability of the correct word here is not equal to 1, in which case it means that the LLM is not exactly confident what the right word is, then what will happen is that you will not have this thing going to 0 and you will not get a 2 to the power 0. You will get something like 2 to the power 1, 2 to the power 2, something of that sort, and then your perplexity will be much higher. Lower the perplexity, better it is. Okay. This the perplexity is the most common metric that a lot of pre-training papers basically mention. Now, there is also task-specific metrics that papers mention, and I wanted to put this on how do you include the metrics or how do you read the metrics. For example, here you see that how many parameters the LLM has, activated parameters, and here you see the performance on this y-axis, right? Now, for LLMs, you have to compare for the same number of parameters which LLM is doing better. For example, Llama 213B, which is a little over 13 billion parameters here, versus Mistral 7B, where Mistral 7B is actually 7 billion parameter model, and Mistral 7B is doing better for the same class of models. It's doing better, right? But if you go higher in the activated parameters domain, then you start seeing models which are doing much, much better, like Llama 370B or Quen 1.572B. So there is a correlation with how the parameters increase and the performance increases, but it is valid only for the same family of models, because as new family of models come up, they improve, they tend to improve, right? So hence these models have a linear relationship within the same family with performance. And here is how usually people report the metric, right? People also report the metric in another way, which is in this way, wherein you can see that some LLM, which is basically closer to the outer circle, is going to be better because it's better at these many subjects, right? While some LLM, which is very close to the uh, center, is actually worse. It's not meeting performance in any domain, right? Some LLMs are closer to the center at some points, like math, for example, this green color LLM, which is Alpaca 13B, closer to maths, center in the maths department, so bad at maths, but good at humanities. Okay. So people tend to report metrics in this way also, wherein you can put some axis on what metrics or what tasks you want to be solved, and then you can report this. Okay. So how do you do human evaluation, right? Human evaluation is done basically using something called as Likert scale ratings, which are basically a popular method where you will be asked about 5 or 10 questions about the LLM response. Is the response understandable? Rate from 1 to 5. Is the response valid? Rate from 1 to 5. Does the response from the LLM give correct facts or not? Rate from 1 to 5. Okay. So this is how it looks like, right? So you would have summarized the following news article, and then there will be a summary written here. Okay. Then you would give a rating and you would give answers to some of the questions like what do you think is the rating for the response? And then you will answer these questions, and based on that, the score will be given to the LLM after you have done this. What do you say? You have done this inference on the LLM's response, right? You have done this uh, gauging the LLM response, and then you get the scores. Okay. Now, there's a lot of challenge in evaluation, right? Like, for example, this one, subjectivity is a challenge. What I might think is not a great response, you might think is a good response, or vice versa, right? I might say something is not a harmful advice, you might say something is a harmful advice, right? Okay, so it can be subjective, right? So subjectivity, because we have a long text coming out of LLM, right? Like a very long thing it writes, and we are trying to evaluate that. So it's people who are evaluating it, and then it gets subjective. Okay, subjectivity is one problem. Lack of standardized benchmarks is another problem, in essentially the fact being that we have few benchmarks like maths, GSM 8K is there, and for some of the benchmarks like MMLU or those are other benchmarks like glue, super glue, they are there, but all domains don't have benchmarks. Like there will be less benchmarks in medical or legal domain, while science domain may have more benchmarks, or coding domain may have more benchmarks. So, and good standard benchmarks are also not existing. Okay. Then another problem is evaluating factual accuracy and consistency. So the LLM may generate a factual answer in one time, and in the next sampling, it may not generate a factual answer or a consistent answer. It may tell something else in the next iteration. Okay, so because sampling from the LLM is probabilistic, right? So you sample one token, then you sample the next token, then you sample the next token. So sometimes in the sampling, it will give one response, in another sampling, it will give another response. Okay. And then the other challenge is balancing multiple metrics for overall performance assessment. So are you valuing high factuality, or do you value how well the LLM writes and how well it formats its output? Or do you value how fast it is giving output? What all metrics do you take into consideration and then call an LLM a good LLM or a bad LLM, right? So similarly, for generative image systems, do you consider a system good or well at generation if it generates very crisp, sharp images, or do you consider it correct if it generates natural looking images, or if it generates, or do you consider it good if it generates very colorful images, right? So this balancing multiple metrics is a hard thing in the current evaluation scenario. I would say that a lot of work remains in how to do LLM evaluation correctly and generative AI evaluation correctly, and it's an active area of research of how to do these evaluations, right? And if we do them well, then LLMs will keep improving further, and they will be very useful in the future if we evaluate correctly. So up next, we'll look at some of the ethical consideration in LLMs and the use of LLMs. So one of the first concerns is data privacy. So how do you ensure that the data that you have provided on the internet is not used for LLM training? Like how do you ensure that you wrote a story which is original to you on your blog post, and now someone scrapes your blog post, trains LLM on your and other data, and now their LLM is writing stories. So is it right for you to have written that blog post and then getting it used in LLM training data? So there are privacy concerns. How do we let people who do not want their data to be used for LLM training opt out? And how do we make regulations around this so that this is not violated easily? that is definitely a ethical challenge and needs to be addressed properly when you are training LLMs or when you are making gathering data. Right. Then there is the challenge of hallucination. So LLMs tend to hallucinate a lot when, let's say, you ask them about some topic and the LLM may not have seen the knowledge of that topic or correctly understood that topic previously, then it may hallucinate an answer, right? Because there is no switch on LLM which says that if you don't know the answer to this topic, don't answer. Okay. Uh, we have that easy thing in our head where we can say that I don't know this. Okay. But LLMs are usually trained to be good assistants. And in that case, a good assistant usually replies. So LLMs will reply, and it is upon us to fact check rather than depending on the LLM to be always factually correct, right? Because sometimes the LLM may not know, but it will still answer because it's trained to be a good assistant. So usually few of the things that we do is one is we keep the training data updated and we add regularly new training data to make sure that the data is accurate and up to date. Okay. We also do some validity check at the end of the output to make sure that if we are calling something out, then it is actually, if the LLM has said some fact or something, then it is actually correct. It's not just a hallucination by the LLM, right? So you can do a post response check by doing a search or some kind of retrieval and checking against a fact database whether the facts that LLM told is actually correct or not. Obviously, that adds latency, right? So there are other techniques, lot of techniques to mitigate hallucination. So one is prompt engineering, where one of the methods of prompt engineering is retrieval augmented generation, wherein you first take the user question and then you do a round of search on a fact database or on Wikipedia, let's say. You retrieve evidences or factual evidences which are relevant to the user's question. You put those retrieved evidences into the LLM's context, and then you ask the LLM to answer. Then you ask the model to answer. So given that it is actually retrieval augmented generation, the LLM has in its context already the facts that are required to answer, so it will not hallucinate because it does not need to hallucinate what about which it does not know. We are just searching and giving it information automatically. So it's just rephrasing. It's not writing an answer by itself. Okay. Prompt tuning and other methods also tend to help with that. Okay. There are model architecture improvements which can help also in this. One is knowledge graph utilization. So knowledge graph utilization basically is you would have a knowledge graph of all the facts and things that you need in your application. Like for example, in medical, you would have a knowledge graph of medicine interacts with another medicine or medicine cures disease. Okay, so entity action, another entity, or entity relation, another entity. You would have a graph of such things, knowledge graph, and use this knowledge graph along with the LLM. So if I ask the LLM, can paracetamol help alleviate my fever? Then the LLM will look at paracetamol from the knowledge graph, it will look at fever from the knowledge graph, and then it will try to see is there a connection or not. Uh, Paracetamol cures fever. If there is a connection like that, then the LLM will say yes. But we have curated the knowledge graph beforehand, and then we are using the LLM on top of it. Okay, so that is one of the ways. There are few other ways also. Okay, external knowledge check, which I talked about just before, that once the output is done, then you check the LLM's output for facts and see if LLM may not have written a correct fact and then correct it post the LLM has given the answer. Okay. There's some of the techniques like chain of thought prompting also, where you tell the LLM to think out its logic before answering a concrete answer so that it has more time and more space to think about what it is going to say. So these things help a lot in reducing hallucination, although hallucination mitigation is an active area still. Okay. Then we look at bias. Okay. Algorithmic bias or potential for misuse. How does bias come in LLMs? Okay. So first of all, LLMs can have a lot of bias based on how the training data is, right? If you train the LLM training on data that has biases, then the LLM will reflect those biases. Uh, what we have to do as a post-training step to reduce these biases and these problems with LLM is that we do something called as RLHF, right? Reinforcement learning from human feedback, wherein we have examples where the LLM is giving a bad output, and then we tell the LLM that this output is bad, and we train the LLM to refuse such questions or completely give a answer where it says that bias and misinformation and those things are bad and it should not do it, right? So we train it in that way after the pre-training phase. But how much can we like do in the second phase, right? Like, can we cover all the biases that could be in pre-training data and mitigate against that, right? Maybe or may not be. We may not be able to mitigate against all the biases that are in the pre-training data. It would be very hard to mitigate the entire set of biases. So obviously that makes it a challenge, right? Because the LLM is using its pre-training data to understand the world and help answer our questions. And our pre-training data itself has biases, right? So again, an active area of research, and there's a lot of work going on in this. Uh, Safety and trust in LLMs and AI is something that is being looked upon by research community as well as by industry, and a lot of companies as well as research labs work on this. So the chance of LLMs doing something bad obviously keeps decreasing over time because more and more safety research is happening. So that's a good thing. Then there is potential for misuse. Like, can I use an LLM for bad purposes? Like, in my opinion, I would say that you can, for example, use an LLM to create spam, right? You can create spam emails from LLMs. Okay, and the LLM will generate very good looking spam emails. So someone will think that it's an actual person writing the email. Okay. You can generate spam comments from LLMs again. You can create deep fakes, which are basically photos of someone's head posted in someone else's body, right? So there will be deep fakes of one celebrity face on some other person's body. That kind of things happen, which is again a misuse of generative AI, right? So preventing this misuse again requires both legal intervention and legal standards, as well as proper tuning of the LLM, and also more awareness among people that you cannot really say that some content that is just written as a comment is truth, right? Like, basically on the internet, you can find a lot of content that is written by LLMs or bots, right? So you cannot believe everything that is written because it could be have been written by an LLM instead of being written by a person, right? So pictures, photos, even videos. LLMs now generate videos. OpenAI, Sora, and some of the models now can generate videos, audio. All these things can be generated fake through the LLMs, and hence everything that comes through a digital media should be taken with a grain of salt, right? And we should be careful on what digital media we trust and what digital media we don't trust, because it could be something generated by an AI system rather than being told by a human. Obviously, human systems, like people, can also say bad things or lie, but with an LLM or with a generative AI system, it can be done at a larger scale. So, laws and regulations and our own awareness will help us protect against it. So, as I was mentioning, right, mitigating these things require multiple strategies. We do something called as red teaming, where we actually put a team of experts who try to talk with the LLM and break the LLM down into saying bad things, and we then try to analyze where the LLM might be uttering bad things, and then we try to patch it up before the LLM is released publicly, right? The other thing is being aware of how to use AI systems ethically and how to detect or protect yourself from unethical AI system uses if someone else is using AI systems unethically, right? So, a good idea of AI ethics is important. And then transparent model reporting to track, right? So, basically, if there is an AI system involved in doing something, it should be reported. Like, if a comment is written by AI, we should mention that it's written by AI instead of pretending that is a human is writing it. right? So those are all the ways. That's again, LLMs are having this problem of harmfulness or of bias, but we are going to use LLMs to solve that also. So LLMs will solve the problem with LLMs. We can train LLMs to detect harmful content. We can detect hate speech, online comments, online toxic comments. We can do these detections with LLMs. So there is a particular model which is an example model in this class of models where LLMs are used to detect this, right? Llama Guard Hit Billion is a model which was developed by a company called Meta. And what it does is it can take a uh, input, okay, and it can then take the conversation, and then based on the conversation, it can say whether the conversation output is safe or unsafe. For example, it can take something like the task and the policies, right? So in the policies, you can basically mention whether something is safe or unsafe, and then you can write the name of the policies, and then it can basically tell you if some policy is violated, right? So this LLM can itself be used to filter the output of other LLMs to make sure that we don't have unsafe output, right? So these are the kind of categories they have used. Okay. But you might need more categories like maybe politically sensitive is something that is not here, right? So politically sensitive content might be important to be added to the set of harmful categories. So as more and more companies do this and train their own unsafe detection LLMs, we will have more and more LLMs themselves detecting the output of other LLMs or unsafe outputs of other LLMs. So I want to talk about the business aspects of this, right? So uh, companies like Amazon or Apple have their own chatbots or assistants, right? Like Alexa or Siri, right? And then there are also specialized chatbots like some e-commerce chatbot or which you have on Amazon, Flipkart, Myntra. They have their own chatbots, right? So, for example, an e-commerce chatbot is much easier to make as a safer system because, see, if I go to other e-commerce chatbot and ask it a question like, should I eat paracetamol for fever? The e-commerce chatbot can simply say that this is not in my domain of expertise and hence please consult a doctor. I cannot help you with this. Okay. An e-commerce chatbot can simply refuse to answer this. And that is a very good and easy method of handling anything, any question that is not e-commerce related, the e-commerce chatbot can refuse. Similarly, any domain specialized chatbot, like a chatbot which is meant for handling technical content, that chatbot can easily refuse to answer a question that is non-technical, or if a chatbot is made to handle issues for, let's say, a company, like let's say Samsung has a chatbot randomly, just saying, just an example. Let's say Samsung has a chatbot which helps you debug issues with your Samsung products. Okay. Then the Samsung chatbot can refuse if you ask it, how is the weather in Bangalore today? It can refuse to answer that because it's not under its domain. But when you have general purpose assistants like Alexa or Siri, their domain is the entire world, right? You can ask them anything. So they cannot just refuse everything, right? So they have to have a much more versatile handling of uh, adversarial questions or bad questions, bad scenarios. They need to have these kind of much more stronger guardrails to make sure that you can ask it a lot of things, but if you ask it something bad, then it can still refuse. So generally, making a specialist chatbot is easier than making a general purpose assistant in case of safety and bias handling. And obviously, there are platforms like GPT, GitHub Copilot. These systems are equipped to handle a broad range of queries, and they would still set some boundaries, but they would have to work on a lot more wider range of things, right? But as I mentioned, industry-specific bots and customer support bots, these can have a much narrower domain and can refuse to answer. So with that, the ethical consideration we have come to an end. We will look at the real world applications and some case studies of LLMs. Okay. So in real world applications, one of the applications of generative AI is to create realistic simulations of various health conditions in medical, or enabling medical trainees and practitioners to practice in a secure, controlled settings. It is also used for clinical diagnosis and drug development. AI, like AlphaFold, is used to basically generate protein structures, and then these protein structures can be used as medicines, and other biological medicinal use cases can be solved very easily with them. Okay, so a very good use case of generative AI, right? Because it accelerates medicine synthesis by a huge amount. So yeah, we talked about this. It's by Google DeepMind that basically generates the 3D structure of proteins from their amino acid sequences. And it is useful because it is helpful in drug discovery as well as in other aspects. Okay. So let's look at some of the real world applications of these LLMs and these chatbots and virtual assistants. And another application, we talked about science applications, but not everything is science, right? So uh, you have ChatGPT, Siri, Alexa, and obviously the customer support bots, right? You might be getting calls from also these LLM bots or these voice systems which are spam calls. So that also is a real world application. And then we have this automated code generation. So uh, GitHub Copilot and tools like uh, this yeah, I mean, GitHub Copilot is a bigger example, but there are other tools also. There is DeepSeek Coder, which is another LLM which writes code, and ChatGPT has data analysis feature. So they are all automated code generation features. Okay. And then we also have music and art generation, which is happening through LLMs and music generative AIs. You have some of these examples. I would tell you to check these out. Perplexity is a search engine which uses LLMs. Character AI is a uh, website which has a lot of LLMs which are made into various characters. So you can talk to Superman or something like that on this. There is also some of these DALI, Midjourney, and Runway ML, which help you generate images and help you generate diagrams and those kind of things. So, like, this is a simple example, which is just for ChatGPT generated. It helps you tell compelling storytelling with DALI, right? Because you can actually generate images based on your prompts, and then using those images, you can stitch multiple images as a story, right? So it helps in storytelling, and then it also helps in songwriting. So, like, this is one. It's coming from this.
Heat classrooms bristling, bags of brain spam, tech buzzing and jostling. Professor pitching algorithms and bytes. Young minds dreaming of tech nights. Coding like demons, mad out freaks. Clicking, submit, and getting no sleep. Neurons fired in cerebral glare. Everyone's just floating here. We are the future, we know what to do. AI kings and queens with a vision so true. Hanging with data, our future so bright. Innovating, the world making it right.
Yeah, so this is completely AI generated. So the lyrics are written by some LLM like ChatGPT, and then there's a uh, text to speech synthesis. And usually the text to speech only utters the speech, but here you can actually see that it's text to speech and music, right? This is suno.com.create, where you can just use your Google login and generate it, right? One more.
tech buzzing and jostling. Professors preaching algorithms and bytes. Young minds stringing the tech nights. Coding like demons, not out freaks.
So the lyrics is same, but the music is different, right? It generates two at a time. Sorry. Some way to go to the next slide, please. Yep. So we'll look at the future of generative AI and LLMs now. So there are some trends that are coming up. One is multimodal LLMs. So as I showed you, you can use LLMs and DALI-like generative AI systems to generate images from text. You can also give text and image as input to the LLM, right? Text and image input to the LLM, and then the LLM will generate output based on both the text and image. So you can also have other things like querying on an image. You'll give an image of some people and bananas and all, and then you'll ask the LLM how many bananas are in the image. So that is multimodality. There is also efficiency improvements that are happening in the entire area of LLMs. We want the LLMs to be faster, consuming less memory, cheaper to put on mobile devices and stuff. So there's work in that area also that is happening. There's something called grouped query attention, which if you have not heard of multi-head attention, multi-head attention basically has uh, queries, keys, and values all multiples, right? In group query attention and in multi-query attention, what we do is we reduce the number of keys and values, and this results in a high efficiency. So this is one of the techniques. There are several other techniques that have been proposed and are being implemented. There is also resurgence of recurrent style networks. So RNNs are coming back. Mamba is one of such models which uses RNNs, but obviously there's some clever tricks that are put in so that the RNN forgetfulness is no longer a problem, right? There's also focus on developing low parameter LLMs, which we can put on mobile devices and run on our laptops. There's also effort on extending the context length. Context length is basically how many words you can put into the LLM at once. And if you are able to put more words into the LLM context, then you can have longer conversations, right? You can also probably put an entire book and ask questions about the book to the LLM. But if the context length is very small, then you cannot do that, right? So extending the context length is one of the areas of research as well. Then there's agents. So agents are basically systems where you don't just have an LLM and a question and answering system, but rather you have an LLM which is operating as one part of the system. But there are also other parts like tools. For example, you will add the web browsing to the LLM. You will add code execution to the LLM. You will add more tools like maybe speech to text and text to speech. So that way you will have an agent, and then it will have a cyclic process that the LLM will first look at some tools or some of the input question, and then after looking at your input question, it will again look at the tools it has, iterate and try to get answer, then look if the answer is satisfactory, then it will give you the answer, otherwise it will reiterate. So this cyclic. So LLM does not get invoked once, it gets invoked multiple times to answer you. And that way, uh, that's what we call an agent currently. But basically the agent is something that tries to use the intelligence of the LLM along with tools and multi-step executions to help you on some task like coding or web search or something like that. Okay. One of my favorite ideas is accurately measuring LLM performance, which we talked earlier also, that we don't have great data sets to measure LLM performance. We don't have a lot of open data sets to measure LLM performance, and we definitely don't have really open and correct ways of measuring LLM performance. So how to measure LLM performance well enough in multiple different areas, that's an active area of research, and definitely more help here is appreciated. So yeah, this something like multidimensional evaluation that I showed you in that circle where you have multiple nodes on that circle and you evaluate the LLM on multiple of those things, and whichever LLM is closer to the boundary of the circle, will be a better LLM, right? I showed you in that colorful circular diagram, right? There are some new benchmarks. This is a long context benchmark. You can actually go to this link and read more about it. There's MMLU Pro and there is LMSys Arena also, which are good new benchmarks. And then the next and the more important problem to solve is high quality data. So we are running out of internet data, and also the internet data is not very high quality. So how do we have data that is high quality, covers more languages, covers more domains and more areas? And how do we also extend the life of that data for training these models? Like, how do we make sure that the data is not polluted with other LLM generated data? How can we do pre-processing to increase the quality, deduplicate the data? Those are all challenges because uh, in the Microsoft Phi series of papers, they demonstrated that training with high quality data it gives you a better LLM at a much less training cost. So this paper is named Textbook is all you need, right? Textbooks is all you need. And they show that training on good text gives you a higher quality model with less training expense, right? You don't have to train it for very long. And yeah, these are some questions that you can ask and maybe discuss it in the upcoming Q&A session as well. So how do we prevent and stop the misuse of AI in creating spam, phishing content, or propagating false info? And then who owns the generated AI content? Like if I am using ChatGPT and generating some content, am I the owner of that content, or is the ChatGPT the owner of that content, right? And if I have generated content using LLM with some of my own inputs, and someone else copies my content, is that a copyright violation or is not a copyright violation? Right. So these areas are still gray areas, right? Then what will be the impact of generative AI on employment, especially in creative fields? Like, are painters going to lose their jobs? Are software engineers going to lose their jobs because LLMs can write code now, right? So these are some of the questions you can probably ask your in the doubt session. Okay. So yeah, we are mostly over time, and thank you very much for attending. I hope you enjoyed the music. So remember, the field of AI is ever evolving, and staying updated with latest research is important and useful. But even more important and useful is to make the right kind of applications. So do research, make some good fun stuff, make some applications using these LLMs and generative AI systems, which can help people, and then provide feedback. Also, feedback link will be given to you at the end of this session. Okay, thank you.